Oh, Keon, did you see the snow? No, because I'm in southern Illinois right now. I'm close to Carbondale. But did it snow in Chicago? Wow. Huh. You sure it's not like, oh, really? A lot? Well, well, I was about to make a terrible dark humor joke. I won't do it. It's nothing to joke about. But anyway, the snow's amazing. Yeah. Wow. No, I've not seen the news this morning, so hmm. That's interesting. Wonder what that's about. A 30 car pileup? Holy cow. Wow, I'm surprised Triton didn't cancel class. Har, 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 har. It was horrible, the video. It's actually 50? Well, yeah, in Chicago, they were all doing 90 miles an hour on the expressway or better, and changing lanes like crazy people. I still remember the night I was driving in Sunday night, and there was like about 30 motorcycles, and they were doing like better than 100, probably doing like 110, 120 on Kennedy, and they were just buzz, 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 like the killer bees attacking. So yeah, all it would take is one person change the lane in front of one of them, and they weren't just quite quick enough, and they'd have been all over the back of somebody's SUV. Anyhow, okay. Well, we're gonna get going on a lecture. Oops, that's not the right place though. How about here? Okay. So we have not finished chapter 15. Um, so we need to do that. And according to what I have, at least according to my notes, we've not finished it. And we stopped off at slide number 5. So I'm going to get down there. So the last thing we did was the stuff about calculating solubility from the solubility constant, the KSP. And make the slide bigger. That's probably too big. Hello, Noah. Anyway, so we did these calculations, and one more time, I'll just remind you to pay attention to what what X is. That in this case, the concentration of the calcium is X, but the concentration of the fluoride is 2 times X. That comes from the formula of the calcium fluoride, the CaF2, and then the concentration of calcium fluoride is the same as X. So anyhow, that was the last thing we did. We stopped there. So we need to talk about this. And this is complex ion formation here. And what it's saying here is that metal ions will act like Lewis acids. Now, we did Lewis acids back a couple chapters ago. And there our Lewis acid was, let's see, boron trifluoride. And that's also what we're talking about here. So BAF3. And then what's called complex ions. And what the complex means is that these are not normal covalent bonds. These are what's called coordinate covalent bonds. I better type that because this is not going to work well if I try to write it. And I'll make it bigger so you can see it better. Maybe I will. There we are. Okay, so the bonds that you get in a complex ion is called a coordinate covalent bond. We'll come back to this one more time, yeah, in a future chapter. But anyway, the idea is that in a normal covalent bond, you're sharing electrons from between two atoms, and one electron in the bond comes from one atom, and another electron comes from another atom. And in this case, for the electrons that makes the bond comes from one atom. So like what we're seeing here with nitrogen in ammonia, there's a pair of electrons that comes from the nitrogen. Hydrogen does not have any electrons, but yet it forms the bond between the nitrogen and hydrogen. So the pair of electrons between them, both of them come from the nitrogen. Same thing happens when we get the bond between nitrogen and boron in this compound over here. The bond between nitrogen and boron is both of the electrons are coming from the pair that's over on the nitrogen. So now that is the basis of a coordinate covalent bond. But with these complex ions, excuse me, what's going on is, again, we have a coordinate covalent bond using a pair of electrons, again with ammonia having a pair, and then the acid part of this is a metal cation, like silver over here. So these are in equilibrium. So there's an equilibrium constant. And the final thing that we end up with is this, except there is a mistake here, and that is this should have a positive sign on it. Because as you can see, the equation is not really in balance. There's a positive charge over on the left. There's nothing that's going to balance that charge, like with the ammonia. So you still have a positive charge at the end. So the coordinate covalent bond there, or excuse me, the complex ion that we have, it has a positive charge. And that's going to be true for some other ones that we're going to see here in a second. Anybody got a question? Okay, we'll go to the next one then. So now what this is a chart of a bunch of different complex ions, and the equilibrium constant is right here, and then the equations are over here on the right. And thing to notice is for these equilibrium, the equilibrium constant is a very big number, like 10 to the 29th, 10 to the 25th. Those other ones are pretty big too. 10 to the 35th, 10 to the 42nd. Now, you remember Avogadro's number, is 6 times 10 to the 23rd. These things are bigger than that. So this means that if you can form a complex ion, you will. That almost 100% of the reactants become the products. So we have this first one that we had in the previous slide. This time it's got the positive charge like it's supposed to. But then we have a bunch of other ones listed here. Like we got one here using cyanide with silver. We got one down here that uses hydroxide with chromium. So anyway, there's a bunch of different examples here. And you're not going to need to memorize anything on here. This is just to give you an idea that these have big values and that they can form these complex ions. So we'll look at how this can affect things in the next slide. So what we have here on the left is what we would have called a insoluble compound if we were in Chem 140, and now in Chem 141, we call these a sparingly soluble compound. So formerly called insoluble, and now called sparingly soluble, meaning that there is a equilibrium between the insoluble compound and what you get. It does dissolve, and there is a solubility constant for that. So formerly called insoluble, like in Chem 140. Now we're going to call it sparingly soluble. So down here we got the, oops, get my marker going. We've got one of the typical sparingly soluble compounds, silver chloride. So in the bottom of the test tube, there's a bunch of silver chloride. It would be a powder. It doesn't want to dissolve. However, a few of the ions do break away. That's what this is showing us in the picture below. But then what we're going to start doing is adding in ammonia, because as we saw in the previous two slides, ammonia can get with silver and make a complex ion. So that's being shown in this picture of where now the silvers, let's see, let's find some of them. Let's see, there's some silvers here. And those silvers are going to get together with the ammonia, and you're going to end up then with your complex ion over here on the next picture. So we're going to go from having our precipitate at the bottom of the test tube to the entire test tube being clear. We're causing all that stuff to dissolve by converting it into a complex ion. And we can take this and use it in doing analysis for metals if we don't know what's in a mixture. That's on this next slide. So this is called selective precipitation. You start out at the beginning with a mix of different metal cations, and then in the first step here, we're adding chloride to it, and we're making some insoluble chlorides over here. So those precipitate out. Everything else in the mixture is going to continue on. So what we're doing there is we start out with a test tube that has our metal cations in there. They're all dissolved. Say they're all nitrates, so they would all dissolve. We add some hydrochloric acid to it, and some of them precipitate. And then you can pour off the liquid from that. And then we can add to that liquid hydrogen sulfide and a little bit more hydrochloric acid just to keep the pH low. And now we're going to get a bunch of sparingly soluble sulfides. They're going to precipitate out. So in each case, we're getting a precipitate. We're getting a precipitate up here. We're getting a precipitate down here. So you're getting a solid in the bottom of the tube. We used to do this experiment last. Anyway, then we're pouring off the liquid that's over here on the other side. It says remaining cations. Now to separate those out, we're going to add ammonium sulfide. Now the pH is going to go up because previously we were putting in a bunch of acids. The pH was low. So we're going to get the base soluble sulfides and hydroxides, or excuse me, insoluble, base insoluble ones. And then you've got everything left. You can then add this other compound, ammonium phosphate and ammonia, you're raising the pH even more. We're getting some other stuff to precipitate out, and then you have a few things left over. So this is an old way of doing this kind of analysis. Now we would just put the mixture in an instrument, and it would give us the amounts of these different metals. But what we're looking for here is things like silver and lead and mercury and cadmium and so on. And that concludes this chapter. Is there a question from anyone? Okay, I'm going to stop sharing that one, and we're going to go to our next chapter, which is thermodynamics. And we did thermodynamics in Chem 140, and at that time, the whole thing was really about things like enthalpy and Petz's law. And let's see, we did some calorimetry experiments. And it was stuff like that. So that's what happened in Chem 140. But now we're going to bring in some other concepts. One of the main ones is going to be entropy, and then also something called Gibbs free energy. We're going to start out with going back and looking at some of the previous stuff from Chem 140, and then we'll be getting over into the newer stuff. So here we go. So this is a illustration of a calorimetry experiment. And so to do a calorimetry experiment, you need to have your experiment in a well-insulated container so as to avoid exchanging any heat with the outside, with the room. So that we're basically creating our own little universe here to observe. And then within the calorimeter, we have the part that's called the surroundings. That's down here at the bottom, and that is generally a solution like water. And then the other piece that what we're really focused on is the system. And that can be either a chemical reaction, or it can be some sort of physical process like melting or freezing or things like that. Now, an example of an exothermic process. Move that down a little bit. There we go. Exothermic process. So when you see exothermic, you want to think about it that the energy is exiting the system. So everything's always in reference to the system. So energy then is coming out of our system and it's going into its surroundings here. But in our surroundings, we can have ways of detecting that energy has flowed. One would be with our thermometer over here. And since the surroundings gained energy, their temperature would have increased, and we would see an increase in temperature on the thermometer. Or if you could put your hand inside the calorimeter, you would feel it as being warmer. Hence the red hand over here. Our next slide is the opposite kind of process. Now we're going to be endothermic. Again, you've got a system. You've got the surroundings around it. This time the heat has to flow into the system from the surroundings. measuring what's going on with the surroundings, we'll see that the temperature decreases. We would also see this as cool. And when you see endo, you want to think that the heat is going into, or endo, into the system. Okay, so this is, we did this before in Chem 140, so this should not be anything new to you guys. But now we get to our first new concept. This will involve some memorization because we're going to go through 3 laws of thermodynamics, but you need to not only know what the laws say, but you need to know what number goes with which. So the first law of thermodynamics is that energy cannot be created or destroyed. All the energy that is ever going to exist currently is existing. The total energy of the universe is constant. It's not increasing, it's not decreasing, it's constant. But of course, the universe is taking in everything. So heat can be flowing from one place to the other, or it can be converting from one form to the other. But in the end, the total energy that's in the universe is constant. So energy can be converted from one form to the other, like chemical energy going to heat energy. It can be transferred, say, from the system to the surroundings, or from the surroundings to the system. But in any case, the total amount of energy does not change. Anybody got a question? Okay, let's look at some more stuff. So now these are the 2 aspects of energy that we're going to be looking at. And we're going to see a little bit later on that the enthalpy and the entropy are together in a particular sample material, but we break them out into enthalpy and entropy. So here we go. So enthalpy, heat is either absorbed if it's endo, or is released if it's exothermic by a system during a constant pressure process. There's no work involved. And you might recall when you did this in Chem 140 that what we're thinking about most of the time is we have a beaker and there's some kind of chemical reaction going on inside there. And we're only considering the heat that is either taken in or released. There's no work going on. Work would involve pressure. And the idea here is that the atmospheric pressure that's surrounding our beaker is more or less constant. So it creates a constant pressure process. Now, if we had a piston and we allowed the piston to move, then we could be converting some of this into work in your automobile engine. That automobile is mostly now, unless you're a essential worker, which if you are, I am sorry, because that's a tough deal. Anyway, our new term is entropy. It's a measure of the randomness of a system. And the combination of enthalpy and entropy is going to determine whether a process spontaneously occurs or would it require some sort of outside action to cause it to occur. But now back to the idea of entropy or randomness. A couple places you could think about on this is like your car again, assuming you got one. Notice how great I draw this thing. And, you know, as the day goes on, you know, you make a run through McDonald's and you throw the wrappers in the back seat, or you, I don't know, pick up some stuff at the convenience store and the wrappers go in the back seat. You know, gradually you're accumulating all this junk in your car. And if you don't exert some energy to remove that, then that's just what's going to occur. That's one sort of example of entropy. Another one would be our living space that we're in. Here we are. And, you know, we do the same sort of thing. Stuff just happens, you know, you just don't know how, but you look back later on and, God, where'd all that stuff come from? So then you have to, okay, it's cleaning day, we're going to clean all that up. So you are trying to overcome the randomness in your system. The human body would be another example of this, that if energy was not exerted in biochemical processes, the breakdown processes within the body would eventually shut it down. And that's another example of entropy. So things tend to head in the direction of randomness, energy being dispersed everywhere, and systems just stopping. So we have to expend energy to keep them going. Okay, let's look at our next slide. Here's an example of spontaneous versus non-spontaneous. On the left side, we got a whole bunch of molecules, and on the right side, we have none because we have a vacuum. And between the two sides is a valve, and the valve is closed, as it says. So there's a barrier between the left and the right side. But if we open the valve, we'll see that molecules flow from the left to the right, and you have approximately an equal number on both sides. The thing about this is if we leave the valve open, we're never going to come back and find that the molecules have spontaneously moved back to where they came from. Therefore, it's an irreversible process. The only way that the molecules on the right could go to the left would be if we somehow pushed them over, like with a piston or something. So that's one example of irreversible. But now here is a process that is spontaneous, but it's also reversible, in that if we increase the temperature above 0 degrees, then it's going to change this sample from a solid to a liquid. That'll happen spontaneously, but it's also reversible. Likewise, if we were to lower the temperature, I'm really using the wrong colors here for this. If we lowered the temperature, then our liquid would spontaneously become a solid. So that is spontaneous, but it's also reversible. And heat flow is another spontaneous process. If we have a hotter object and a cooler object, heat is always going to flow from the hotter object to the cooler object. So in our first picture here, we have two different temperature samples, a high one and a low one. I don't know why they didn't just call it cool, but they did that. And then if we move them into contact with each other, the heat will start flowing from the left side to the right side. And in the end, you'll hit thermal equilibrium. The hot ones are not as hot as they started, and the cool ones are not as cool as they started. They both had the temperature change, and it's going to be approximately the same temperature. Never are we going to have a situation where the heat flows back over to the left spontaneously. That's not going to happen. Okay, so this is irreversible. Now back to our entropy thing we were talking about earlier. Entropy is a measure of the randomness of a system. It's a state function, meaning that if we're going to calculate it, we take what is the final entropy, final randomness, we subtract from that where we were to begin with. Okay. This gets us to our second law of thermodynamics. Again, remember that you got to keep the number with the law. And that says that the entropy of the universe is going to increase. Remember, we said the energy of the universe is constant, but the entropy is increasing. So what it basically is saying is that the organized energy is going to become disorganized as time proceeds. And this is what causes a spontaneous process to be irreversible. We've got a math consideration down here, the same thing. Reversible process, if you're comparing the system and the surroundings, if you put them together, they're going to cancel each other, the system and the surroundings. It's going to go to zero. But in the other hand, if it's an irreversible process, then that total is going to be a number greater than zero. So now getting closer to something we can actually use is statistical thermodynamics. And statistical implies a probability. Because we can never, say exactly where the energy is, but we can assign a probability to it. So this is going to relate what we're going to call the molecular properties. So in other words, these are for individual molecules to the properties of a large number of molecules. So say this is many molecules. Is bulk. But now back to the molecular level here. We get to something called a microstate. That's a single possible arrangement of the position and the kinetic energy of a molecule. So where is the molecule and what is its energy? We're going to be looking at those individually on the next slide. But if we were going to do the whole calculation of this, we'd be calculating. We're not going to be calculating any of that. This is more of a conceptual thing that's going to help you later on to be able to state if a particular set of circumstances is going to cause a reaction to be spontaneous or not. So keep in mind what this is really all about. You're breaking up at times. Oh, that's not good. Okay, when you say repeat, you mean this slide or the whole thing? Oh, okay, gotcha. Thank you. Okay, I'll do it. I'll just erase that and do that again. So I don't know why it's not working well. On my end, it says things are okay, so I don't know. It's the internet. Anyway, statistical thermodynamics. It's statistical, which is talking about property. This connects properties at the molecular level with properties at the bulk level. Bulk means many molecules. And then the next part of this is microstates. That's a combination of the position of the molecule and its energy. And I was saying, I think, that the reason why we're doing this is it's going to allow us to predict how how spontaneous, let's put it that way, how spontaneous a process will be. But some things are going to cause it to become more likely to be spontaneous, and others it's going to cause it to be less likely to be spontaneous. And we're going through it, in a conceptual level, because that should help you to be able to just look at a description and say, oh yeah, that's going to be spontaneous, or no, that's probably not going to be spontaneous. Okay, so going here, this is sort of like a, it's sort of like what we were doing up here with, where molecules, over on the left side there, on the left picture here, they're all on the left side, and then after we open the valve, they're on both sides. What we have here is we have two locations, the left and the right. We can have all of molecules on the left, or we can have all of them except one, and it can be a different one. So this is just showing us all the possible arrangements for position. Or we can have half of them on the left, half on the right, and then it can just be a different set of the two. And we go to finally down here where they're all on the right. Well, another way to look at this is that, let's say that the left side is low energy and the right side is high energy. We could say all the molecules have low energy, or all the molecules have high energy, or these other variations in between. So each of these is a microstate. So if we went through and counted all these, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we've got 16 microstates illustrated here. Okay, now we're going to use this to look at some different conditions that we can apply to our process and see how that would affect our spontaneity. Oh, sorry, I got one more slide I need to do before we quite get there. And this is showing us mathematically how this works. So we've got W here, and that's the number of microstates. So like before we had 16. Entropy is the measure of how many microstates are associated with a particular macroscopic state. Here is an equation that hooks those together. Entropy is related to the microstates. Through this function here, you've got a constant, and then you've got natural log. We don't really care about this part here. We could just say that the entropy is proportional to the number of microstates. So if we increase the number of microstates, we will increase the entropy. And if we decrease the microstates, you're going to decrease the entropy. So like it says at the bottom here, more final microstates is going to give you a greater entropy. So now we're going to go through some different conditions that we can apply to a process and see whether it increases the entropy. And you need to be able to predict whether these would increase the entropy. Our first one that we're going to consider is volume. If the volume increases, then there's more possible places the molecule could be. Hence, more microstates, increased entropy. That should be pretty easy to think about. So if we went back to here, instead of having just two boxes, we could have 4 boxes or 16 boxes or something like that. And as you give it more boxes, then when you're going through this process of where is the molecule or what energy is it at, you have more possibilities. So you have more randomness and greater entropy. Okay, let's look at something else then. Temperature. If the temperature increases, the average kinetic energy is going to increase. And this is going to give you more possible molecular speeds, which is going to be more microstates and increased entropy. But let's look back over here as to how that increases the number of speeds. We've got a graph here, and on the left side is 0 energy. Now, you should consider that there is no negative energies. Okay, you cannot have a negative energy. Oops, that would not be possible. So you can't have a number less than 0. Okay, so that limits, that constrains our left side of our graph. Now what we have in our graph is 2 different temperatures, T1 and T2. So you can think about, in both of these cases, that there is an average energy. That would be the midpoint of this bell curve. And then we'd also have one for the other temperature, and that'd be the midpoint of that bell curve. We have a fixed number of molecules. So because we have a fixed number of molecules, both of these curves should have the same area under the curve. Okay? So at temperature 1, its midpoint is here. The left side cannot go any further than 0. And since it's a bell curve, it's going to be sort of symmetrical. I mean, if it was a perfect bell curve. So you should have the same on the left as on the right, or I should say it the other way around. Should have the same on the right as you have on the left. If we go for a higher temperature, you still have the same number of molecules. So the curve is going to be squatted out. We're flattening the curve. Not the same kind of curve. Anyway, in this case, with temperature 1, the left side still can only go to 0. This curve is supposed to be symmetrical. Therefore, the right is going to be somewhere over here to try to make it equivalent to what we had on the left. And here's the take home. This whole thing, I'll change colors. The range of kinetic energies for the lower temperature is this right here, where I'm drawing the blue line. The range of temperatures for the higher temperature, oops, change color, it's going to go from 0 all the way up to here. So because this is basically because you cannot have negative energies, with a higher temperature, you're going to have a broader range of possible kinetic energies. Anybody got a question? This is one of the, seems like it's usually one of the harder things to think about. The main thing is, if you increase the temperature, you're going to have more entropy. Okay? Okay, let's look at another condition that will affect entropy. If we have a solid, the molecules are totally restricted to that solid. They've got to stay within the cube. They can't go anywhere else. When we melt it into a liquid, now they can move around some within the liquid. They can't go above the liquid, but they can move around within the liquid. And then if we heat it further, producing a gas, they are totally free to just go anywhere. So they can be more random. So as you go from solid to liquid to gas, you're going to increase your entropy. Now you can think about this if you have a chemical reaction where you start out with something as a solid, but after the reaction occurs, it's now a gas. That reaction is going to have an increased entropy, and that could cause it to become spontaneous. We'll see there's more to come with entropy that we have to also include the enthalpy. But for now, what we could say is if we have a reaction that goes from a solid, oh, now it says my connection's bad. Guys, I don't know if you can hear this or not, but it says my connection is bad. I'm trying to give it a moment to see if it's going to get better. Oh, you can hear. Can you see the slides, Yulia? Oh, okay, cool. Then I'm not going to worry about where you can see me. You got my little, you got the mad scientist. Anyhow, it is breaking a little. Oh, okay. Well, I'll tell you what I'm going to try to do is I'm going to see if I can connect through my phone instead of Wi-Fi, because for some reason sometimes my phone works better than the Wi-Fi. Here we've got a beaker that's got NO2. So NO2, it's got two of the NO2s. The coefficient is 2. On the other side, on the product side, we've got 2 nitrous oxides and 1 oxygen. So altogether, we have 3 molecules. So if we are increasing the number of molecules, if we increase the number of molecules, then we're going to have greater entropy. And this could cause the reaction to be spontaneous. Once again, we have to also look at what's going on with the enthalpy. Okay? And now, next slide. Oops. Before I do that one, has anybody got a question on these? I'm gonna run back through them real quick. If during a process we increase the volume, we're going to increase the entropy. If during a process the temperature increases, it's going to increase the entropy. If during a process we go from a solid to a liquid to a gas, we're going to increase the entropy. And if we increase the number of molecules, we're going to increase the entropy. Okay, now we're to our third law of thermodynamics. Make this slide a little smaller. Well, nope, not that. Okay, there we are. So, third law of thermodynamics, remember, one more time, got to keep the numbers with the law, says that when we're at absolute zero, there is no motion in our molecule. Therefore, there's only one microstate, and the entropy is zero. So, absolute zero, no motion, one microstate, entropy is zero. Now, how the entropy is zero, you can see mathematically. Remember this equation we had before, that the entropy is proportional to the number of microstates. So if we're taking the natural log of 1, it's going to give you a 0 regardless of k. So the entropy is going to be 0. And then what we're looking at over here on the right side is a heating curve. We're starting out with our sample at 0 degrees. Therefore, the entropy is also going to be 0. And then we're going to raise the temperature of the solid until it starts to melt. Here's where it's melting. Temperature is not changing, but its entropy is increasing because we are going from a solid to a liquid. Then if we continue to heat it, we will raise the temperature of our liquid now, which is also going to be increasing the entropy because we said higher temperature, greater entropy. Then we're going to continue to heat it, and it's going to convert it now from a liquid to a gas. That will also increase the entropy. We continue to heat it some more, and we're going to raise its temperature, which would increase the entropy. Okay? So now what we have in this table are what's called standard entropy, standard values for S. And this is going to bring in a couple more points of how we can predict how the entropy is going to be. We've already seen that, liquids are going to have a higher entropy than solids. Gases are going to have a higher entropy than liquids. So if we look at our chart over here, which I will need to make bigger so we can see it. We've got the solids at the bottom here, and we've got the liquids just in the middle here, and then we're going to gases. And if we look at these numbers in general, the numbers for the solids are smaller. I mean, I realize this iron chloride's pretty big, but the rest of them are, like 2-digit numbers. And then you're going to bigger numbers when you go to liquid, and then you're going to even bigger numbers when you're at gases. So that fits that whole idea. Now, the next thing, though, that we can get out of these is that the entropy is going to increase with the molar mass. So if we were to compare, say, nitrogen and oxygen, N2 molar mass is 28, and O2 molar mass is 32. So the oxygen has the higher molar mass. And if we compare the entropies, the entropy is larger for the oxygen. So that fits with this idea that if you have a higher molar mass, you're also going to have greater entropy. Now, another one we can look at is the number of atoms that are in a formula. So for this one, let's look at, let's compare water to, this is methyl alcohol. The water has 3 atoms in the formula. The methyl alcohol CH3OH has 4, 5, 6 atoms. So it's got more atoms in the formula. And then if we compare the entropy over here, you can see that it's going from 188 up to 237. So it's also higher. So if you had to rank some molecules, you could do that, rank them for their entropy based on their molar mass or based on the number of atoms. Okay, anybody got a question there? Okay, let's look at some more stuff. Okay, we're getting to Gibbs free energy. This is deriving Gibbs free energy. You're not going to do that. Of course, that would be maybe physical chemistry class. But the formula down here at the bottom is the Gibbs free energy equation. And you're going to need to remember that. That will not be given. You're going to need to know it. So we'll go to the next slide because we're not going to have all this other stuff to interfere with looking at it. So Gibbs free energy, delta G, is the product of the enthalpy and the entropy. So there's the enthalpy, there's the entropy, and then we have the temperature in there, and remember that it's got to be in Kelvin. Okay, so you can calculate the Gibbs free energy by taking the enthalpy if you know what it is, taking the entropy if you know what it is, and then using the temperature. Now, why does Gibbs free energy matter? Well, it is pretty much the way we know whether a reaction is spontaneous. So something happened to this slide whenever I put it into Collaborate. I don't know what the deal was, but anyway, the deltas, the triangles became capital D's. And so remember, those are deltas where the D is, not your slide on Blackboard should be correct. So anyway, if the Gibbs free energy is negative, then the reaction going forward, going from reactant to product, it's going to be spontaneous. So this is really the important part of what we've been doing here. Negative Gibbs free energy reaction is spontaneous. And it's spontaneous going from the reactants to the products. If the Gibbs free energy is 0, then the reaction is at equilibrium. And while the forward and reverse reactions are still occurring, they're occurring at equivalent rate, and therefore it appears like nothing is changing. Then if the Gibbs free energy is positive, the reaction is non-spontaneous in the forward direction. Again, going from left to right. However, it is spontaneous going in reverse. So the reverse reaction, in other words, going from product back to reactant, is spontaneous. So remember, Gibbs free energy negative, reaction is spontaneous. And if you can remember that, then you can get the other ideas from that. That if it's positive, then it must not be spontaneous. And if it's spontaneous going forward, it's not spontaneous going in reverse, or the other one. If it is not spontaneous going forward, then it is spontaneous going in the reverse for these equilibriums. Okay, let's look at one more. Here's a table that's sort of putting all that together. And unfortunately, it doesn't actually have the Gibbs free energy equation. So let's see if I can type this up in a reasonable amount of time. Okay, delta. No, I got to flip back and forth out of US and Greek characters, so it takes a little while. Fortunately, I only got 2 deltas to deal with. Oh, that's not true. I got 1 more delta. So let's make that bigger. Okay, so there's your Gibbs free energy equation. Oops, I got the sign wrong. Oh man, that's not good. Okay, that's supposed to be a negative right there. I wonder if I can cover it up. Maybe that'll work. Okay, everybody, just imagine that's a negative there. I'm sorry, I messed that up. I don't want to type it again. Well, anyway, if we look at the equation, if the enthalpy or the delta H is less than 0, which is the same as saying it's going to be negative. So let's put a negative up here. We'll put that in parentheses. So regardless of what the actual number is, if the sign of that number is negative, and then if the entropy is, sorry, I'm doing the wrong one there. Get rid of that one. I think I can do this. Yeah, I can. Okay, let's draw it around this one. If our entropy is greater than 0, in other words, that's saying that, okay, it's positive. And we put those up here. Then you can see what we're doing is we're taking a negative number, and then the negative sign here is going to change the positive to a negative. So we are combining a negative with a negative. Therefore, you're going to end up with a negative value for Gibbs free energy. And what we said before was negative Gibbs free energy is going to make the process spontaneous in the forward direction, no matter what the temperature is. Okay, I'll give that a chance to sink in. If the enthalpy is negative, and if the entropy is positive, then you're going to end up with a negative Gibbs free energy, and that's going to make it spontaneous at any temperature. And then if we have the opposite situation, where the enthalpy is now positive and the entropy is now negative, then the process is going to be non-spontaneous, no matter what the temperature is. And then what we have in between is these two situations where the temperature will matter. In one case, it'll be spontaneous if it's a high temperature because it will make the positive entropy a bigger value after you combine it with temperature. And in this other combination, if the entropy, if the entropy is not favorable and the temperature is a low number, then that's going to decrease the impact of the entropy, and the reaction could then be spontaneous. Now we're going to do this on some worksheets, and I think that will help clarify what's going on. Let me see what the next slide is. Yep, we don't want to do that yet. So this is what we want to work on right now. So I'm going to go to our worksheet for this. And so you guys, if you go into Blackboard and you go to course materials, you're going to see the worksheets. And so you ought to be able to, with those, you should be able to open one up and then you can fill it in. And so this is the Gibbs free energy worksheet. I'll tell you what, in a second here, I'll show you where that's at just to make sure you can find it. But anyway, what you want to do is fill in this table, answer some questions. There's another question in there. So you're looking for the worksheet that is like this, that says Gibbs free energy at the top. I'm going to share my desktop and show you where that is. Okay. So if you click on course materials, scroll down some, you find worksheets, and you go to the one for thermodynamics. Then you go to the, okay, Gibbs free energy 1. That's the first worksheet. You can see this is the same one I was showing you. So when you get into your groups, you'll be able to get to that. And then I want you guys to fill this thing in, discuss amongst yourselves the answers, and then I'll come back and poll you guys to see how that came out. So I'm going to stop sharing my screen, and I'll put you guys in the groups. Let's see if there's any, yeah, I've got a few more people that I need to move around. Oh, wait a minute, did it, oh. Well, because of all the problems with the internet, it dumped everybody out. So I've got to put you all back in again. If you see I put you in the wrong group, just, tell me, I'll move you. Okay, finally. Okay, I'm going to start the groups up now. And if you have a question, you'll need to text me. I won't be able to hear you, but you can send me a text. So again, if you notice you're in the wrong group, let me know. I'll move you. If you got a question, let me know, and I'll get back to you. Okay, here we go.